Training massive AI models requires thousands of processors operating at peak capacity for months. Scaling these architectures means confronting hard physical limits. The primary constraint on modern AI hardware is the von Neumann memory wall. This is the structural separation between the logic units executing math and the physical DRAM storing the network's billions of parameters. To perform a calculation, electronic processors must constantly shuttle activation data across tiny copper buses. Moving this data consumes over 80% of total energy, rather than the actual logic operations. Pushing electrons generates friction, creating arsenales and unavoidable resistive heating. Executing a single matrix vector multiplication, or MVM, using copper wiring incurs an energy cost measured in picojoules. When deep learning algorithms require trillions of these multiply-accumulate cycles every single second, the resulting heat output becomes massive. Between the soaring power draw per chip and the cooling infrastructure required to manage it, the traditional approach to scaling electronic AI hardware has hit a ceiling of practical sustainability. Hybrid photonic neural networks address these electrical constraints by shifting the computation medium from matter to light. Instead of relying on the heat-generating transport of electrons, this new architecture encodes data into continuous photon propagation. Standard logic gates must wait for a centralized clock cycle to flip transistors on or off. Photonic networks rely on passive electromagnetic wave interference. The calculation occurs continuously as the light travels, requiring 0 clock cycles to process the data. Because photons travel through dielectric waveguides with near-zero resistive losses, the power required for a single operation drops from the picojoule scale down to mere femtojoules. This optical efficiency is specifically engineered to target linear transformations, the y equals wx matrix calculations, that account for 90% of a deep neural network's computational workload. Executing these linear operations in flight at the speed of light neutralizes the data movement bottlenecks inherent to von Neumann architectures. The process begins at the input interface, where digital neuron activations are mapped onto coherent laser carriers as precise phase shifts or variations in field amplitude. These light beams feed into a Mach-Zehnder interferometer, the core block of optical computing. When split, phase-delayed, and recombined, the waves exhibit constructive and destructive superposition. The resulting light intensity calculates the exact weighted sum of the inputs. Engineers scale this input capacity using wavelength division multiplexing, injecting hundreds of distinct light wavelengths into a single fiber simultaneously. While high-density copper traces struggle with bandwidth saturation, optical multiplexing easily sustains terabit per second aggregate input data streams. Because light waves of different frequencies do not interfere with each other, WDM achieves multidimensional parallelism. It processes thousands of independent data channels in the exact same physical footprint, entirely free of crosstalk. To calculate massive neural networks, arbitrary weight matrices must first be decomposed into singular value components that match the physical layout of the photonic hardware. Using specialized mathematical decompositions, like Clemens or Rex schemes, these values are mapped directly onto a dense physical 2D array of cascaded MZI units. The individual synaptic weights of the neural network are physically programmed into the mesh via relative phase delays. As the input lasers propagate through the grid, the light passes through all computational paths concurrently. This yields true quadratic, or ON-squared, hardware throughput. Digital SIMD architectures are forced to queue logic through sequential instruction dispatch. The optical grid performs the entirety of the matrix algebra simultaneously as a continuous wave. Synaptic weights, activations, and the multiply-accumulate hardware are completely co-located. This collapses the intermediate memory buffering and reduces data movement to its theoretical minimum. Purely optical computation excels at linear algebra, but it currently lacks the compact, low-loss hardware required for nonlinear activation functions like ReLU. Attempting a purely optical deep neural network runs into severe analog precision limits. Sub-wavelength phase errors amplify across layers, degrading accuracy. To maintain precision, the system must cross back into the digital domain mid-network. This crossing is handled by an optical to electrical transaction layer, built directly into the silicon utilizing high-responsivity germanium avalanche photodiodes. Upon completion of the optical math calculation, these photodiodes instantly convert the interference patterns back into electrical currents that are directly proportional to the computed activations. These analog currents feed into 3D stacked FPGAs, or ASICs, which apply the required nonlinear mathematical functions and execute the closed-loop backpropagation updates needed for training. Isolating the massive linear matrix workload to photons, while deploying electrons specifically for nonlinear control logic, provides a pragmatic engineering path for commercial deployment. Early attempts to scale silicon photonics ran into a critical barrier: cumulative phase errors cascading across massive million-element MZI meshes. Standard photonics rely on thermo-optic tuning, generating heat that bleeds into adjacent components and distorts neighboring optical calculations. To prevent failure, legacy systems burn up to 30% of their power running complex recalibration loops to stabilize the matrix. To solve this substrate bottleneck, manufacturers like QANT utilize a completely different material platform for their chips: thin-film lithium niobate on insulator. This material allows the hardware to shift away from heat-based phase tuning, substituting it with highly precise, direct electro-optic switching. By eliminating on-chip thermal crosstalk, TFL noise substrates allow for scalable, room-temperature operation with ultra-fast modulation speeds reaching tens of gigahertz. These breakthroughs in material science have moved photonic computation out of laboratory theory and into active semiconductor foundries. The resulting hardware, such as the QANT native processing server, is packaged as a standard 19-inch rack-mountable unit equipped with Wi-Fi CIe Gen 4 interface. This chart details the raw power requirements to execute an 8-bit logic operation. Standard CMOS processing consumes roughly 2,300 femtojoules. The thin-film lithium niobate optical equivalent requires just 76 femtojoules. Across deep network inference workloads, this yields up to 30 times greater energy efficiency and accelerates processing speeds by a factor. The architectural roadmap for these processing servers projects throughput scaling from current baselines to 100,000 giga-operations per second by 2028. These metrics are secured without relying on the difficult, diminishing returns of shrinking transistors. Instead, the performance gains stem directly from executing native, nonlinear logic directly inside the physical properties of light. Current homogeneous GPU clusters demand severe power density constraints and immense thermal management. Because photonics eliminates I²R resistive heating entirely, operators can secure massive increases in compute density without installing specialized liquid cooling infrastructure. Despite operating on entirely different physical principles, these optical units deploy into standard data centers, accessed via familiar C++ and Python APIs, sitting on standard x86 software stacks. As latency drops from nanoseconds down to picoseconds, the hardware easily supports safety-critical edge applications, from real-time high-frequency trading algorithms to the microsecond perception cycles of autonomous vehicles. Deploying trillion-parameter models across dense AI agents requires a computing baseline that does not scale exponentially in operational cost. Scaling AI to exaflop capabilities requires a hardware architecture that does not waste 90% of its energy on data movement. The transition from moving electrons to mastering the physics of light provides that path.